Okay, yes. Yes, now it's please, Ali. Yeah. Hello, everyone, and welcome to this talk. I'm Ali Ajrian, a PhD candidate in Computer Network Groups, University of Basel, and today I'm going to talk about introduction to multi-party computation and universal circuits. The computation is the most important or interesting part for me, which is private function evaluation. So let's quickly uh, see the agenda. I don't want to talk about all the multi-party computation technologies, but only focus on garbled circuits. Probably most of you are familiar with this. I will review that. I will talk about how we garble a circuit, how we evaluate the garbled circuit. Then I switch to universal circuit, which is a general circuit that can simulate any circuit up to a certain size. And then we will use this two building blocks to talk about private function evaluation. Okay, for universal circuits, I cover how we can construct the universal circuit and how we can program a specific target circuit onto the constructed universal circuit. So first of all, let's clarify the problem. Again, I don't want to talk about all possible scenarios. I focus only on two-party communication protocols. The scenario is as follows. We have two parties, Alice and Bob. Each of them has a private input. Here, private means that each party don't want to reveal the value of that, the actual value of this input to the other party. They don't trust each other. And also, we have a function f that takes these two private inputs and computes an output value. The important thing here is that the function f can be represented as a Boolean circuit. So we can, during my talk, we can imagine f as, for example, addition of two 64-bit numbers or multiplications, or more complicated function. But for simplicity, let's focus on addition, for example. So the thing is that in this setup, the function f is known by both parties. The only two private things is the input value A and the input value B. Let's say I have the value 5 in my mind and you have the value, I don't know, 10 in your mind, and we are interested to know the summation of these two numbers without knowing the other party input. Although this is a silly example, since if you know the summation by the end of the day and your number, you can subtract and reveal my value. But let's say there is this function doesn't hold this property, and you cannot inverse the output value. Okay. So as I already mentioned, the function is public and is known by both parties. So we have two rules. One is garbler, the other is evaluator. One of these two parties garbles the circuits and values, and the other party takes the garbled circuit and these garbled values and evaluates and computes the garbled output. So the output is a garbled value. Here, we will modify this circuit, generate the garbled value, garble these two A and B, and then the evaluator will compute the garbled output. Okay, what do we mean by garbling a circuit is that, so for each wire, actually we have a Boolean variable, right? Each wire can be, from the perspective of Boolean algebra, it can hold a true or false, a 0 or 1, vice versa. Then there are since there are two possible values, we should somehow encrypt these two values. Here, since we don't want exact encryption, we use the term key instead of encryption. So here, since we have two potential true-false values for this wire, we use two different keys for this wire. One representing false, the other one represents true. The same thing holds for all wires. The garbler must generate these entire key pairs. But the thing is that to evaluate the target output, the evaluator must obtain one of these two tags for the regarding truth value. For example, if the target value here for this wire is 0, he must obtain A0. Same thing for this input value, and then by some computation, the garbler, the evaluator, must obtain this wire tags. The thing is that the evaluator only reveals some part of this input tags, but others must be computable, having a subset of these wire tags. Let's say we are going to compute this function for input false and true. Then the evaluator must obtain A0 and B1, and by the end of the day, what is the output of 0 and 1 is 0. Must obtain or compute B0. So here the challenge for the garbler is a clever design such that if you start filling these tags, by the end of the day, you obtain the right output tag. So the first time Yao formulated this or solved this problem as follows. So for each gate, let's restart. First, you can generate these random tags independently, okay? Two random tags, lambda with random keys or tags for this wire, for this wire, for this wire, and this wire. No problem. But to let the evaluator to obtain the valid tags having a subset of these, we compute these 4 ciphertexts based on the functionality of the gates. For example, here we have an OR gate that from the truth table of an OR gate, we know that OR of false and false must generate false, meaning that if I fed A0 and B0, the output must be C0 in terms of keys, right? So then, if I put A0 and B0, the output must be C0, meaning that I can encrypt C0 along with the L bits of 0. I will come to that later. But if I consider the functionality, I encrypt C0 here. So for the next one, I mean A1 and B0, OR gate must generate true, meaning that the key A1 and B0 must generate C1. So then I encrypt C1 this time with these two keys. Is that clear? So we do the same thing for all the gates. And the key point here is that after generating these 4 ciphertexts, we must randomly shuffle them. Otherwise, the evaluator will know what were the input tags. We do the same thing for the AND gate. As you see here, the AND gate generates true only in one case. If the input value is true and true, the output must be true, meaning that A1 and C1 must generate the key D1. So then D1 is encrypted with these two keys, A1 and C1. For all other possibilities like A0, C0, A0, C1, A1, and C0, we encrypt D0. Yes?
Clarify what was, I'm kind of confused with the tag is what C0 and C1 or exactly?
Lambda bit numbers, random lambda bit numbers. Okay. So here in normal situation, you have one bit value, but we encode this one bit value with L bits random numbers. Okay. So far so good. Now the question is, we should be able to obtain valid output tags fitting specific inputs to our circuit. How we can handle that? Let's say we are interested to compute this function for a equals 1 and b equals 0. So remember, the input must be private. So the evaluator must get these corresponding tags on an oblivious way. Otherwise, it obtains the input of other parts. Okay, there is some magic. I won't talk about that. It is called oblivious transfer. Let's say these tags with some magic have been asked to the evaluator. So the thing is that since we want to set this wire as true or 1 and this wire as false, then corresponding keys will be transferred to the evaluator. So A1 and B1 are delivered to the evaluator, and now evaluator has these ciphertexts and these two input tags, and his or her task is to compute these wire tags. Okay. So how he or she can do this? So adding this ciphertext, they decrypt this ciphertext with what they have. So for this case, we have these two tags or keys. Then we decrypt these four ciphertexts with these two keys. Since the key is A1B0, this decryption will generate some random number, right? The keys are invalid. What about this one, A0B1? Since it has been encrypted with A0B1, but we are going to decrypt that with A1B0, again, we see a random number. But for this one, A1B0, this one was encrypted with A1B0, and here we have A1B0. If we decrypt with this ciphertext, we generate this. How we can detect that it was a valid decryption? Here is the place that these zeros will help us. Since this number is, at the end of this number, we see L bits of 0, we can detect that, okay, this was a valid decryption. Okay? So then we throw this part away and C1 will be obtained. Is that clear? Okay? So this way, we have computed this tag without knowing this represents true or false. This one also represents true or false. Okay? So what about the next case? We do the same thing. Now we have C1 and A1 and these four ciphertexts. Again, we decrypt all these four ciphertexts with A1 and C1. So obviously these three will generate invalid outputs. How we can detect they are invalid? By the pattern of the output. Since they don't end to L bit of zeros, then they are garbage. We throw them away, but this one is valid output and we detect B1. Okay. So this way we evaluated the function without knowing which input is true or false. And also what is the corresponding Boolean value of the output tag. So as I already mentioned, to transfer input keys, there is oblivious transfer magic. We don't talk about that in this lecture, but you can consider it in a very high-level perspective. That oblivious transfer is like a black box. You put two values into that box, and then can obtain one of the two values without knowing what is the other one. And you don't understand which of the two I took. There is this box in cryptography. Okay, we can also generalize the entire setup to any function. And the thing is that we do the same thing. It doesn't matter how the circuit is complicated. Every wire is encoded into Boolean values of every wire is encoded into two random tags, and then for each gate, you generate 4 ciphertexts.
Here we're seeing, it's okay for me to interrupt, but here we're seeing a polytype function, and actually any function could be garbled in this way, right? So I'm guessing the reason you're mentioning polytype is because you can garble it in polytype. Like the obvious version will keep the
you can garble the function by polytype function. I mean, you can garble it in polynomial time. Yeah.
Wouldn't the function, like the circuit, become so large that the security properties of the encryption function won't work anymore?
You mean the size of the circuit?
Yeah. What if the circuit is exponentially large? Wouldn't that be a problem?
Yes, it is a problem. I mean, you must be able to garble that in polynomial time, meaning that the size of the circuit must be polynomial.
Yeah, because we were implementing this as part of a project. We tried it worked for all circuits, but for SHA 512, it was so bad it took over an hour to just do the garbling of the function.
Yeah.
But for all other circuits, we were able to implement optimizations and turned out to be, well, there was some fish.
Good. So this is the very original version of garbling approach, but there are some optimizations. You can make it much better than this. For example, one is point and pair news. The thing is that for evaluation, we must decrypt all the 4 ciphertexts and then check which one is ending to L with sub-zeros. We can prevent that if we cleverly assign some random indexes into each wire. Then we can at evaluation, we can exactly decrypt the target ciphertext. Instead of 4 ciphertexts, we can decrypt only 1 ciphertext. The other optimization is row reduction. So instead of generating 4 ciphertexts, we can generate 3 ciphertexts if we cleverly design random tags for each wire. And the output, we can manage one of the ciphertext always be 0. Then we don't have to send it to the other party, I mean evaluator. The last one is free XOR. Instead of independently generating random tags, we can somehow correlate them by XORing one of the tags with a global offset, meaning that the key pairs, one is randomly generated, and the other one is to generate the other one, you XOR the first one with a global offset. This optimization will generate faster or better result, but in overall, the overhead is, as Amar already mentioned, is huge. Like it needs a huge amount of computation. Okay, so as I already mentioned, one of the key limitations of garbling is that, similar to homomorphic encryption, the function f is publicly known by all the parties. So the inputs and outputs are private, they are garbled, but the function is known to all the parties. The question is, what if we want to go one step further? Not only the inputs are private, but also the function f must be private. The scenario is as follows. Let's say, again, think about a two-party situation. I have a specific algorithm, and you have a specific data. For example, I have a very perfect algorithm that detects some health problems in your body, and you have your genome. You don't trust me to share your genome to me. I don't trust you, or I don't want to reveal my algorithm. So then in this situation, the function must be private. The input also must be private. So we can do that by garbling a universal circuit. The same thing holds, except this time, instead of garbling the circuit, we garble the universal circuit. And then the function is mapped to a beta stream. We will see that. And my input also will be another beta stream. Then these two beta streams will be the inputs to the circuit, garbled circuit. Okay, so now it is time to talk about universal circuits to achieve this property. So what is a universal circuit? A universal circuit, as the name suggests, is a special kind of Boolean circuit that takes as input a sequence of configuration bits and simulates a target circuit. Let's say you have a target circuit C, then you find the proper configuration bit for this circuit, and using this configuration bit, you configure the universal circuit. From now on, this universal circuit behaves like the target circuit. In other words, if you set these configuration bits and get the input X to this universal circuit, it behaves like C of X, the target circuit. So this universal circuit is constructed from a bunch of configuration gates and a network of switches for routing the connection among the configurable gates. So I should talk about three elements. Two types of switches and one universal gate, as I already mentioned. So the first type of switches is very simple, X switch. As the name suggests, with a configuration bit C, you can set the circuit to forward the inputs with the same order or switch the order. For example, here, if you set C equal to 0, X0 goes to output directly, X1 also goes directly. If you set the configuration bit to 1, the order will be switched. The Y switch, on the other hand, takes two inputs and generates one output. It is a simple MUX, multiplexer. So you have a configuration bit again, like here. If you set it to 0, X0 will be routed to the output. Otherwise, for C1, X1 will be routed to the output. So far, so good. And the third element is universal gate. The purpose of a universal gate, as the name suggests, is to simulate all possible two input gates and or X or whatever. So we can construct this by three Y switches like this. Since we are simulating all the possible 2-bit gates, there are 16 possible such gates, 2 to the 2 to the 2. So then it must have 4 configuration bits and 2 input bits, right? For example, for AND, we have 2-bit inputs, and then we set configuration bit to 0, 0, 0, 1, then this box behaves like an AND gate of X1 and X2. So here is a table for configuration bits. For example, if you set all the bits to 0, configuration bits to 0, it always returns false, regardless of values of X1 and X2. Or for true, you must set all these values to 1. Okay, so now we are breaking this box. Universal circuit, again, was a circuit that takes an input, a configuration bits, and then behaves like a circuit. What is inside that? It is consisted of 3 different modules: X switches, Y switches, and universal gates. So the plot here I generated, I represent X and Y switches. No, X switches with this shape, Y switches with this, and universal gate with rectangles. As you see, every X switch has 1 control bit, Y switch also 1 control bit, but every universal gate have 4 control bits plus 2 input bits. And it generates 1 output bit. But here, for example, you see there are 2 outputs. Can anybody guess what is the scenario here? Exactly. So this output is connected both to this and this. Okay. So okay. So a universal gate, as we saw in the 2 slides before, behaves like a 2-input gate, or it can behave like a constant value, false or true. In other words, it can simulate inputs and gates. Okay, so for a gate with some inputs, each input will be simulated by a universal gate. So the previous picture is not the perfect picture. So universal circuit doesn't take 2 different inputs. It actually takes 1 input, that is configuration bits. In other words, we set the inputs of the target circuit in the configuration bits. Since every single universal gate can behave both in the role of universal in a binary gate or an input. And the thing is that by setting this configuration bits of X and Y switches, we can route how these universal gates are connected to each other. Okay, and by setting this configuration bits for every universal gate, we can set how the universal gate behaves. Is it an AND gate? Is it an input equal to 0 or whatever? So let's consider a very simple example, a 3-gate plus 2 input circuit. As you see here, input 0, input 1 are fed into an AND gate, then the output of AND gate plus this input generates this output with this XOR gate, and then it is gone through this NOT gate and generates the second output. So if we want to implement this circuit on top of a universal gate, first of all, we should model any of these gates by a universal gate, right? Also, these 2 inputs must be simulated by a universal gate. So since we have 2 inputs, these 2 inputs will simulate these two universal gates will simulate these 2 inputs, and we have 3 gates. These 3 universal gates will simulate the AND, XOR, and NOT gates. The first step is very straightforward, right? So we have this. Okay, I will configure this with that table. If I want AND gate, this is, I think it was 0001. I put 0001 here, and it becomes an AND. But the complex part is that then how I connect or make this connection. So I want this to be connected to this, meaning that, or this must be connected to this, meaning that this must be connected to this. right? This will play the role of this AND gate, and this will play the role of this input. So I need a connection here. How can I make this connection? I must configure X and Y switches. This task is challenging. I will cover that later, but let's first complete this example. To model this or simulate this on top of this, this is the configuration bit, or PC, as we already saw here. This PC will be this sequence. So this one will model this one. If we want to compute this circuit for true and false inputs, the first 4 bits for this will be 1111, since true configuration bits is 1111. For the next one, this one, which plays the role of the second input, we want to set it as false, meaning that, okay, we should set 0, 0, 0. Or for example, for AND gate, this one, which becomes this one, we need 0, 0, 0, 1, etc. And the other things that are not colored are the configuration bits for routing network, right? And one thing about the first 2 bits can be set randomly, since they are not important. Okay, so now let's again see our problem. Let's say we have a circuit with I inputs and G gates. Then we must construct a universal circuit with I plus G universal gates, right? Since every gate and every input is simulated by a universal gate. So how we should construct such a universal circuit? The second question, how the routing network must be constructed? Where should we put an X switch? Where should we put a Y switch? And again, how they must be connected. How we can then program such a universal circuit. Okay, the short answer is graph theory will help us. Okay, so here I assume that all of you are familiar with the common terminology of graph theory, what is called vertices, node edge, in degree, out degree, this sort of things. If there is question, please interrupt. I use this notation for a directed acyclic graph written as a DAG of degree D containing n nodes. If we have a DAG with n nodes and the maximum input or output degree of such a DAG is D, then we use this notation for that. Yeah. For example, this is a DAG containing 5 different nodes, and the degree is 2, since the maximum input degree for this graph on these 2 nodes is 2. So then we denote this by DAG 2, 5, 5s. It's 35 minutes. Okay. Thank you. So, to construct universal circuits, we define a new mapping that is called edge embedding. And edge embedding takes a graph and maps it into another graph. This is a small graph, this is a big graph, G and G prime, such as every edge inside the small graph can be simulated or mapped to a path in the other graph. So, since here we have 5 different nodes in the bigger graph, we need 5 nodes to play the role of these nodes. And every single edge in this graph will be mapped by a path in the bigger graph. So we call these nodes in the bigger graph that is called edge universal gate. We will come to that. And we call them poles. So here we have in the original circuit graph, we have 5 nodes, but here we have more than 5 nodes. Some of them are called pole, that simulate these nodes. The other plays the role of routing for us. Okay, the next term is edge universal graph. A graph that can edge embed, the previous definition we had, can edge embed any graph with this amount of nodes. If this graph has n pole, then it can simulate or edge embed any graph with n nodes. Another condition is that these two must match about their degrees. If this is degree 2, then the degree of poles must be 2. Okay, as you see here, this is our original circuit. Its corresponding graph is this one, representing input nodes and gates by some nodes. So node 0, node 1, node 2 is this AND gate. As you see, 0 and 1 are fed to node 2, and then it goes to the next gate, etc. The thing is that since we can edge embed this into this, if we can construct from this a universal circuit, this means that we can simulate this by the corresponding universal circuit. That is the case. So it means that construction of a universal circuit is reduced to construction of an edge universal graph. If we can generate an edge universal graph for the corresponding graph of the circuit, then we can construct universal circuit for that. So from graph theory, we have this König theorem that actually this is the result of that, any DAG T with n nodes can be decomposed to d graphs of degree 1 with n, each with n nodes. Yes, consider this graph again. This is a graph with 5 nodes and degree 2. This theorem claims that we can decompose this graph into 2 graphs, each with 5 nodes, but each one is degree 1. At most, input or output of all the nodes are 1. So here, as you see, I colored the 2 graphs on this one. So consider these nodes with these green edges. This is the first graph, and the second one, the same nodes with these 2 edges. Is that clear?
So the criterion is that the union of the 2 yields the original?
Exactly. You can decompose or the other way. You can construct from it. So this is done by edge coloring. So, and the König theorem appears here. That from this, I can construct this graph, a bipartite, undirected bipartite graph. As you see, all the nodes are listed, 5 nodes, and their corresponding nodes. Here we have a connection from 0 to 2, then from 0 to 2 prime. From 1 to 2, 1 to 2, 1 to 2 prime, etc. Then if we color this graph, it means that we have already generated this graph. Okay.
And I asked Eric, you're now at 40 minutes.
Mhm.
You allocated a full hour for Ali's presentation. You allocated 60 minutes or 45 for Ali? 60 if you, it's just weird.
No, it was 1 hour, so there was a bit of wiggle room.
Okay. So now 40 minutes, up to the hour would be 20 minutes to go. If it's only 50 minutes, it's just 10 minutes to go.
Okay, yep, can handle intense, yeah. Okay, based on this edge coloring theorem, we can decompose every graph like this, degree D graph, into D degree 1 graphs. Okay? So this means that if this is the corresponding graph for our target circuit, we can decompose it into D circuits. Meaning that if we can edge embed any of these graphs into a specific kind of EUG graphs, I mean degree 1 EUGs, then we can construct EUG degree n by n samples of degree 1 EUGs. Similar thing for the circuits. We can construct this circuit, degree 2 circuit, by 2 degree 1 circuits. Similar thing for edge universal gates, edge universal graphs. We can construct degree D edge universal graph with D samples of degree 1 edge universal graphs. Here you can see the picture. I want to construct EUG degree 2 for this example. I mix 2 degree 1 EUGs and generate a degree 2 EUG. So how we merge these two? We keep the poles shared between them, but union all other nodes and edges. So then, if we can construct EUG1, we can construct EUGD. Now our problem turns into construction of EUG1. How we can construct EUG1? This is a very tricky approach. To construct EUG1, we can recursively handle that. If we can construct for a very short number of nodes, for example, 2 or 4 or whatever, then recursively we can construct for any number of nodes. So this is Valiant's approach for construction of EUG for 2 nodes and 4 nodes. Then by recursion, we can expand it. For example, if we need n nodes, we make the entire n nodes into n over k groups, and then any of these k over n groups containing k nodes, for example, if k is 2, each of these groups will be mapped to one instance of these things. Then having these nodes, again, we have the same problem, how we can construct an EUG with this new item. Again, we categorize them into groups of 2 and continue. In my implementation, to construct this, you see here that I grouped nodes 2 by 2. Then again, the same problem for these 3 nodes must be handled. Okay, these 2 again are constructing a new setup, new EUG, and the last again a new EUG, and recursively I handle that. So now that we have constructed EUG1, it means that we constructed EUG degree D, meaning that we constructed universal circuits. having universal circuit, now the problem is how we can program the target circuit onto this universal circuit. Again, to program that, we handle the programming by graph theory. Again, the recursive approach is applied here. Since it is much more complicated than construction, I won't cover it fully, but I put some part of my code here that how recursively you can construct a routing for that. I think I have forgotten to put routing in that slide. Maybe. Yes. As you see, for this graph, if you want to edge embed this graph into this edge universal graph, we need a routing from node 1 to we need an edge between node 1 and 2, meaning that we need a path from pole 1 to 2, from pole 1 to 2. And I think
want to do right. Right?
Yeah, I use colors.
P1, then write down the.
Yes, P1 to P2. Yeah, with this stuff. Exactly. And for the rest, also, there is colors representing that. So this is done by a recursive function. And then how we can construct universal circuit from a universal graph. It is very straightforward and easy task. Every node with in degree 2, out degree 2 will be replaced by an X switching. Degree 2, in degree 2, out degree 1 will be replaced with Y switching. In degree 1, out degree 2, it is actually repeating the wire, so it is only a connection. In degree 1, out degree 1 is just a simple wire. So now we have two very powerful utilities. One is universal circuit. The other one is garbled in this case. So as I already mentioned, if we want to privately evaluate the function on top of on a private input, we use a garbled universal circuit. So we construct the universal circuit, we garble that, and then the inputs for the garbled universal circuit will be fuse bits or programming bits of our universal circuit. Okay, thank you very much for your attention.
So now we have the tools to do that, but doesn't the theory tell us about the black box of obfuscation? So does this like circumvent this somewhere?
So in black box obfuscation or entirely in obfuscation, nothing is necessarily encrypted. But here we have this privacy guarantee. So these problems are somehow orthogonal to each other. Yes.
Sorry, was there a limitation on the secret function, like how big that can be, or?
So what do you mean, how big that? For practical implementation, you mean, or?
Yeah. So the universal circuit needs to be larger for larger functions, or?
Yes.
Yeah. Okay. So you have to give up the information that your function is about this large.
For example, I have implemented the full stack of everything. In Python, and for 64-bit additions, it was around 120 milliseconds for a single addition. For production multiplication, it is more than 1 minute. Since, for example, some numbers, the number of gates that you require to generate a universal circuit for multiplication is 1.3 million gates. Yeah.
All right.
Any other questions or comments?
Have you considered implementing that in an FPGA?
Thank you.
No. No, this is not focus of my research, but I don't know. Does this makes the computation faster, or by by a considerable factor? Because at the worst case, everything must sequentially, layer by layer, must be processed, right?
Right.
So then I think it would be a constant factor.
Okay, maybe I'm missing some detail there. Was the cool thing about circuits rather than implementing it in Python is that you get massive parallelism on the inputs. And sure, you need to evaluate it still layer by layer, but on an FPGA you can evaluate like millions of gates.
That's
layers can be really massive.
But at the end, I think it is like every layer is dependent on the next layer.
Sure.
So then, from my perspective at least, it is like a constant factor. Not it doesn't change the complexity class of problem.
No.
Otherwise, for every hard problem, you could implement it on a hardware.
Just a big constant problem.
Exactly.
Maybe another.
But the thing is that we are talking about a single operator, like addition or multiplication. Still, if the constant is 1/billion for large enough or real-life programs, it is still huge amount of time. And then consider to program a FPGA for each function and these overhead. Yeah.
Programming is pretty quick.
Well, my question stems uniquely from the fact that FPGAs are universal electronic circuits, and we're talking about universal theoretical circuits, so bridging that would be elegant, if not efficient.
Yeah. Unfortunately, I don't have enough experience working with FPGAs or these things, but it could be the case. Good. Thank you very much.
Can you say something about the motivation that why you look into that and
Yeah, sure. So we are actually it's a long story, and I should summarize it into 2 or 3 paragraphs or sentences maybe. So the thing is that we are thinking about metamorphic software design, where your software must the input output must be private. The thing is that the function must be private. The signature of function, not only the function be private, the signature of function also must be private. For example, there are some something similar to antivirus engines that, based on some signatures, can detect your function. Again, the same attack is valid here. You can detect. So the thing is that we need a lot of these sort of properties for metamorphic software design. First of all, we don't know yet how many of these properties are sufficient to call a software metamorphic. But still now we were thinking about regular obfuscation techniques that are practical by our daily computers. But unfortunately, in the summer, we set up a theory that proves this approach is not possible. With these normal techniques, you cannot achieve that. Then we try to go in cryptographic approaches. And now we are thinking for a circuit that is executed on a universal circuit privately, what I already talked about, and mutate itself. like this configuration, this must be mutated. We are not still sure that whether this solves the problem or not, but this is another trial.
I'm curious about the term metamorphic, and then is that, I don't know how, like, it seems like that's about changing at the meta level. So is this that you can like change the program into something else so that it becomes obfuscated or something? And then is that at all related to homomorphic encryption, or are these like totally different terms?
They are completely irrelevant.
Okay, so what is metamorphic?
Oh, very good question. I'd like to know as well.
So to be honest, in my annual PhD defense, I tried to came with a definition. For the first year, I tried to formulate that based on obfuscation, since we were hoping that we can handle the problem. But after the results we obtained, the summer that no, this way is completely not achievable. Then we postponed the definition. If you ask me what is metamorphism, I don't know. Now I don't know.
So the definition is fast question. Is what we're doing now going to work it out?
So maybe something that might be more kind of cultural, if I would say form shifting, there's no way the same program looks the same at each step. It will constantly change, so that any way to detect, oh, I have seen that program, I want to eradicate it from the net, will fail. Every time you see the program, it has changed. So the program itself has to be part of the input. So the last picture that we have, where Alice gives the program and Bob gives the parameter, changes that the program and the input goes through that circuit, and what comes out is a new version of the program that you can put in the circuit. But you cannot say is it the same program as the one before. So initially, the metamorphic was meant in that way that it morphs all the time, or constantly morphing would be maybe an approach. We had a big discussion over lunch about this is an intuition, and the team members are still struggling with that, the same as I do. We try to see how far that intuition will carry us. But it seems an important element to have in the future where the censorship on the software will or is already a threat, and that is the ultimate goal. How can we prevent any censorship on the software level? And maybe uncensorability. And we might have, if Osman is ready, talk an element on that. So that is a little bit on the context. And still, we are exploring now with universal circuits. Do we find a path that might fulfill our hope for that metamorphic, however we want to call it?
Yeah, so why wouldn't you call it polymorphic, and what would be the difference in the terminology?
Yeah, I mean, one element of the discussion that we had was that maybe you want to change the function over time. So the function is not only a constant, and then it would be polymorphic, just many forms of the same thing, but it can reflect about, oh, should I take in that new functionality, or should I drop functionality, or should I just pretend to do some computation, but internally I have died. So it has another level also of possibility of influencing its own future. But again, this is a lot of kind of metaphorically trying to capture what would be needed. We still explore these concepts. I think you and then Rocha, if I'm not mistaken.
So metamorphic is metaphoric.
Okay, so the first thing I thought was the idea of the program outputs itself reminds me of the Quine thing. And then the second thing was just when you finish, you say, well, maybe the program changes. It seems like these are orthogonal issues. The one issue is you want to change the shape of the program, but it keeps doing the same thing. But the issue of I want a program that changes itself based on changing requirements or something is something that makes sense even in a normal computing environment. So I think if you just had a program that changes itself and then put that in an anamorphic engine, then I'm not sure you need to think of these at the same time. That's, I think, what I'm trying to say.
And a naive question for clarification. Take the same program and encrypt it multiple times with different input parameters.
Can you say slowly?
If I take the same program and I encrypt it multiple times with different input parameters, then don't I also get like different representations of the same program?
Does this say you have to include your own decryption to then yourself re-encrypt with a different key over and over and over again? And that circularity, we have already started to look into that, that we have the decryption and re-encryption part of that shifting. Yeah, it's that is one approach we also look into. And there is sufficient to just XOR with some random string, or then how you have it, then you need a random number generator inside. But all these things we can now try to disentangle and create building blocks for them. Yeah. So that was a little bit to motivate why Ali presented that a little bit. Otherwise, it looked a little bit just, okay, just for fun, let's go for university graduate fun. We hope really to get something out here. Thank you. Any more questions on that? We are time-wise or now.
Make a comment.
Yes.
So my hoping pulling it a bit more into your space would be if we define what the function operation did, and the evaluation is deterministic of the function based on the input and the previous hidden version of itself, but that changes over time. But we don't know which message is going, or which next input is going to be handled. Then we could have something like a smart contract on the blockchain, or something that just like takes the next version of itself and one of the inputs, and then produce the next one, but the person making this evaluation could be anyone. Because then you could always verify that the process, without knowing what the evaluation was, that it did the computation properly. So then you could have a kind of a secure, replicated chain of states of the function happening over time, and then you could replicate that and have anyone participate in the evaluation process. A bit of some of your initial impulse was like, we're always looking at the data structure or what we can do with this, and then we have the algorithms or the operation we do and then publish. But what if we wanted to hide it as well, but then still have all the nice properties that you get otherwise and be replicated? Thanks.
Just a minor comment on metamorphic, then it seems like computer viruses are an example of an amorphous software array. Have you considered looking into researches of computer viruses?
We have started from it.
I was reading something from the 19s, like virology 101 or something was called.
I'm not sure I expressed that in the group, but the biggest success story, if we would be able to create an alternate that cannot be destroyed. Right, we are that in this very
Really, Christian, you want to make that your like public story? You want to do like a button say on your
Wirehouses or wirehouses? Well, you've just changed what that is.
Everybody's free.
Well,
I guess.
yeah.
Okay, so definitely good for fall.
Thanks again, Ali. Thank you very much.
Fair enough.
And with all the people here on board, we could join some kind of scheduling session. With some input, I think we have.
No recording?
Oh, yes, I should stop that. We can train that. Not